Hi guys. So we're going to go ahead and try to get started here. So what I'm supposed to be trying to do in this video is give you notes for, let's see, what are we doing? Lecture 4, homework 1, and homework 2. Now, I'm not going to go in too much detail for homework 1, just because we need to move on, and so that's just how it is. But let's go ahead and get started. So homework 1, the topic is this: functions and symmetry. Functions and symmetry. Okay, so we just really have a bunch of kind of definitions in here and basic topics, and you don't need to understand everything in here perfectly well at this point. You just need to kind of get through what you can of the homework and move on to another topic. It's just kind of one of those things in a calculus class or any other class really, where when you're in the class the first few days and you're working on review stuff, you can't review everything, and so you just have to do your best. And that's what we're doing here, is just kind of reviewing some basics of functions. So let's start there. Functions. Functions. All right. Now, I'm going to sort of define a relation first, and then I'm going to talk about a function. So even though I wrote functions, I'm going to write a relation. A relation is just a pair of values. That's it. Now I say values, but technically it could be two things of any sets. So like, for example, here's a relation. If I say example, and I write 3 comma A, 2 comma B, 1 comma A, this is a relation. Okay, so any kind of thing that you can relate just two values, like the 3 and the A are associated with each other. The 2 and the B are associated. The 1 and the A are associated. And that association, you could say, those are related. 3 and A are related. And so it's a relation. It relates elements of one set, like the 3, the 2, and the 1, to elements of another set, like the A, the B, and the A. And if you do that, it's a relation. But it's not necessarily a function. To be a function, actually, let's not do that. How do I erase this? Let's figure it out together. Like this? No, that was highlighting. That's clear now that I look at what it just did. This is an eraser. Okay. Yeah, all right, that worked. So that's a relation. Now, what is the domain of a relation? So a domain is just the set of, I'm going to say the first element of the pair But normally what you're going to see for the domain of a function is that a function has an input and an output. And so you would say that the domain is the set of inputs. Okay, so if we look at this relation that I defined up above, that's still on the screen, for that example, the domain is the set of the inputs, but the inputs are the first elements of the pairs. So what are the first elements of the pairs? Well, there's a 3, there's a 2, and there's a 1. And that's the domain. Okay. Now, a range, oops, back there, a range is going to be the set of second elements in the pairs. In terms of a function, we would call that the set of outputs. We don't really have inputs and outputs yet, so that doesn't need to make sense. So the range is the set of second elements. So if I'm going to go back to my example and say what is the range, is a set. So curly braces for a set, so that's why I'm writing it that way. And we want all of the second elements of the set. So let's look at it. What are the second elements? A, B, and A. Well, we don't have to say A, B, and A again. We don't have to say A twice. If we say it once, that's enough. So what are the second elements? A and B. What happened to my A? Pin went weird. All right, so that's the range. So it's that easy. The domain is the first elements and the range is the second elements, and you don't have to list things twice. Okay? Now that is a relation, but I wrote function here. Okay, so what is a function? So a function, I'll change the color, go black. Function. A function is a relation where no input, which are going to be the first values, remember, is associated with two different outputs. Okay, and so no input is associated with two different outputs. So the way you're going to see that in terms of examples, which of the relations is a function? All right, I'm gonna give you just two of them to pick from. So my first one is gonna be curly braces. Let's go 1, 3, 2, 4, 3, 3. And I'll give that a name. I'm gonna call that F. And then I'm gonna do another one. We're gonna call it G. And I'm gonna say 1, 2, 2, 3, 3, 4. There we go. So we have two relations here, okay? And what I'm asking is, which of them is a function? And so the way you check if you have ordered pairs like this listed is, so the function won't reuse any, that doesn't look like any, no, oh, sorry, won't reuse any inputs. And remember, inputs means the first value in the pair. All right, so you just look at the list here. And, oops, okay, so a function won't reuse any inputs, first values. So I look at the inputs of the first one, and they are 1, 2, and 3, right? 1, 2, 3. That's fine. So it's a function. And then I look at the inputs of the second function here. 1, 2, 3. Again, they're all different, right? 1, 2, and 3 are 3 different numbers. So that's a function. So I thought I was going to do one where they were not both functions, but I accidentally wrote 2 functions. So let's write one that's not a function and see how that goes. So if I write a new one, so if I say 1, 2, 2, 3, I'm not doing it again, I promise, 1, 4, oops, like that, then this is not a function. Okay, and the way you can tell that it's not a function is because there and there we reuse the input value of 1. We reuse, the input value of 1. So we used 1 twice. That means not a function. Okay, and it's as simple as that. Now, the thing to keep in mind, though, is that we reuse the 1 twice, so it's not a function. But we're only looking at the first values, right? It says the function won't reuse any inputs, right? And up here, the definition says a function is a relation where no input is associated with 2 outputs. It's not the other way around. It doesn't say that an output is not associated with 2 inputs. So if you look down here and you see that on the function g, no, not the function g, on the function f, there's a 3 right there and there's a 3 right there. We reused the output of 3 twice. That's fine, right? The definition says no input is associated with 2 outputs. So no input value can be used twice. But the output values can be used twice. So having 3 here and 3 here, that's fine. Having 1 here and 1 here, that's not fine. Okay? So that's how you would tell if something is a function when you're looking at a, what's it called? A list of ordered pairs that defines the function. Okay? Now, the way you're used to seeing function is by graphs. Functions on graphs. Right? So a function might look something like this. There's something. All right, so I'm going to do, let's see here. All right, so let's say that this is a graph of f, and then this is a graph of g. All right, these are not both functions. One of them is a function and one of them is not. Okay, when you graph a function, right, like think about graphing these points here. Like if you were graphing this function, which is not the f that I did graph, but if you were graphing this, then the 1, the 2, and the 3 are x values, and the 3, the 4, and the 3 are y values. Okay, and the fact that 3 is used twice doesn't matter. But on the one that's not a function, the 1, 2, 2, 3, 1, 4, the 1, 2 and the 1, 4 is what makes it not a function, right? Because we reused the 1. Now, what that looks like, if you think about where these would be, the 1, 2 and the 1, 4, if you graphed a function, if you graphed the values, the way it would look is something like this. 1, 2, and then we got 2, 3, 4. 2, 3, 4. So if you graphed this not a function, you have 1, 2, which is right there, 2, 3, which is right there, close enough, and then you have 1, 4, which is right there. All right, and what is not allowed in a function is this, right? That was where we reused the 1. And so if something is not a function, it can't have points that are one above the other one. If you ever have a point that's above another point, it's not a function. Okay? So if you apply that to these graphs and you say, does this second graph here have any places where one point is above another point? The answer would be yes, lots of places, right? Like right here is above right here, which is above right here. That's 3 points, right, that are above each other. That's just like this right here, just like this. And that's not allowed. So the fact that if you draw a line through it like that vertically and it hits in 1, 2, 3 places, that's bad. That makes it not a function because we reused an x value, and reusing an x value makes it not a function. Not a function. Okay. Now, the first graph, with the graph of f here, there's nowhere where the same thing happens, right? Like this kind of thing here doesn't happen on the graph of f, right? No matter where you put like a line, right? No matter where I put a line, a vertical line through that graph, it only hits one place, one place, one place, one place, one place, right? That makes it a function because no x value is reused. Function, not a function. Okay, and what we just did there was called the vertical line test. So it's a pretty simple idea. I'll write it down. So vertical line test. We just did it, but the rule is if a vertical line hits or can hit the graph in more than one place, the graph is not a function. Okay, so that's the vertical line test. So the second graph here, G, fails, and the first graph passes, right? So second graph not a function because a vertical line hits in more than one place. All right, and that's some of the stuff you need to know about functions. I've got the homework loaded up, and I'm going to babble nonsense for a few seconds here while I get to some problems I haven't seen yet. Sorry. I'll sing you a song while we wait. No, I'm just kidding. I won't do that. Okay. What else can we do with functions? Lots of stuff, right? So, no, I don't want to do that either. I wish I could pause this video, but I can't. Okay, let's do one of these. So something that you need to be able to do, and I'm not really going to explain it, but I'll do an example. So let's say I have given a graph of y equals f of x, solve for f of x equals 2. Okay, and then I'm going to draw you a graph. Okay, so what do I want to do? I want to go 1, 2, 3, 4, 1, 2, 3, 4. I'm going to put some points on here. I'm going to put this point, 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 this point. Okay, good enough. So I'm going to connect the dots here, hopefully. Okay, so it's not a pretty graph, but there we go. That's my y equals f of x. Okay, and I want to solve for f of x equals 2. So when they say, so if the graph is y equals f of x, and you want f of x equals 2, I mean, think about what this is saying. If you say y equals f of x and f of x equals 2, then aren't you saying you want to know where y equals 2? Right? Because y equals f of x and f of x equals 2. So y equals 2. Yeah, right? And so y equals 2. So you find y equals 2 on your graph, and we're going to look for the x values. So y equals 2 is right here. Right? So if you just think about putting a line across y equals 2, like that, and you say, well, where does that hit? Hits right here and right here. So those two places where the y value is 2. And so those two places are x equals 0 and x equals 4, right? So the y value is 2 at 0 and 4. So the graph is y equals f of x. You want f of x equals 2. That means y equals 2. Where does that happen? Answer, x equals 0, x equals 4. There you go. All right. Now, that was if f of x equals 2. You should be able to just also use a graph to just evaluate a function. So like if I say just something like this, using the same graph, I can just say find, let's say f of 1 and f of 2. If I say to find f of 1 and f of 2, then this is backwards from what we just did, right? Here I said f of x equals 2. Here I say f of 2. So that's a different thing. Here it's the x value that's 2. And here it's the x value that's 1. So how would you get f of 1? Well, again, it's the x value that's 1. So you come to the graph and say, well, here's where the x value is 1. So this is the point that we're talking about. And what you want to know is what is the y value right there. And, what would that y value be? Well, if this is 1, that looks like 1/2 to me, right? So come down here and say f of 1 is 1/2. And then we need f of 2. F of 2 equals, what's that? Well, same thing. We're going to look at the graph and say, well, here's where we're looking. Oh, well, look at that. It's just the same y value. So that's also going to be 1/2. There you go. So you should be able to do problems like that. If they give you the y value, you should be able to find the x value. And if they give you the x value, you should be able to find the y value. All right. Now, kind of related to that, I didn't realize I was assigning this, but I did. you need to be able to just solve a quadratic function for some reason. So I'm just going to do an example because it's there in your homework out of nowhere. So they give you something like this. They say, given, oops, given g of t equals t squared minus t minus 1, solve g of t equals -1 for t. Right? Now this would be a much easier problem if g of t here was a line, but instead it's a parabola, right? Because it's second degree. But that's fine. We can solve a second degree equation. You've done it before, I'm sure. So if you're trying to do this, they say solve g of t equals -1. Well, if g of t is -1, you're going to replace the g of t here with the -1. So you replace the g of t with -1, and you're going to get -1 equals t squared minus t minus 1. All right, so this is our solution. After you do that, how would you solve this? Well, there's specific steps for solving a quadratic that you should follow. So step 1 is going to be move everything to one side. Everything to one side. So the way you'll do that here is you'll just take this 1 minus 1 and you'll add 1 to both sides like that. After you add 1 to both sides, you're going to have 0 equals t squared minus t. All right? Well, then what are you going to do? Well, the next thing you're going to do is factor the quadratic. Now, factoring a quadratic can be hard or it can be easy depending on the form. In this case, it's easy. So all you would have to do here is say, well, you've got t squared minus t squared minus t, but they both have a t, right? So you can factor a t out. And you would have t minus 1. All right? Now, once you factor it, then what you're going to do is set each factor equal to 0. So you've got to factor t, and you've got to factor t minus 1. So you do those separately. So you have the t equals 0, and you have the other factor t minus 1 equals 0. So you set each factor equal to 0 and solve. And solve. All right, so you solve these both separately. So on t equals 0, there's nothing to do. On this one, you would just want to add 1 to both sides and get t equals 1. And that's it. So your last step would just be to answer. What's the answer? T equals 0, t equals 1. Okay, and if I did that right, then that would be the answer. So why are you doing this in this homework? I don't know. It's just what they decided that you're going to do. Oh no. All right. So let's see here. Another thing I want to do, I think I almost need to be just done with this section and move on. So I'm going to talk about symmetry and even and odd, even though there's a couple other things in this section that they're going to want you to do. So I'm going to say even and odd functions. All right. So even and odd functions have definitions. So here's a definition. A function is even if f of x equals f of negative x. Having said that, I'm going to rewrite it though. I'm going to move the minus. I'm going to actually erase all this. If f of minus x equals f of x. Okay? For all x. Even. Now, a function is odd if f of minus x equals minus f of x for all x. All right? So those are your definitions of even and odd. And you can apply them algebraically just by checking this condition or checking this condition. If you do that, you will find out if a function is even or odd. Now, it's important to understand some functions are neither. Right? So this isn't either or, right? It's not even or odd. It's even, odd, or neither. So some functions are neither. Let's try one. I'll just do one right here. I think I can fit it on the bottom of the page. Example. Is f of x equals, I'm going to say 2x cubed plus x even, odd, or neither? All right. So how would you check it? Well, hopefully you see that in the definitions, both of the definitions require you to evaluate f of negative x. And it's the other side of the equal sign, the right side, where they have different answers. So how will you start? You'll evaluate f of minus x. So start by evaluating f of minus x. And then we'll see what we get. So what's f, first of all? I need to write it down so I don't have to keep scrolling up. So f of x is 2x cubed. I don't know why I couldn't see it a minute ago. All right, so that's my function. Now what I want to do is evaluate f of minus x like I said I was. So what's f of minus x? Well, f of minus x is replacing all of the x's with minus x. So you have 2 parentheses minus x cubed plus minus x. Now when you work out f of minus x, make sure you use parentheses like I just did. Otherwise, you're going to make sign errors and screw up. Now, after that, you need to figure out what's going on here. Now the main thing that you need to know is this. Like a negative x to any even number is just x to the even number, right? Like negative x to the 2, for example, is just x squared. And that's because when you do negative x times negative x, right? A negative times a negative is a positive, and you end up with a positive there. But when you have an odd, negative x to an odd number, it works out to negative x to the odd number. So what you need to know is basically just powers, right? Whether you're going to get x to the even or whether you're going to get negative x to the odd, right? So the odd functions, odd powers have a negative there. So you don't want to have to think about it too hard. So when I'm doing this right here, I go, okay, 2 is 2, and then I have negative x to the 3. Well, I know that because 3 is odd, I can just basically drop those parentheses and just have negative x to the odd. So times negative x to the 3. It'll be negative. And here there's nothing to do. It's It's just negative. So you work it out, you get negative 2x cubed minus x. And the idea is that you want to be comparing now this to this. So if the signs on every term match, f is even. If the signs on all terms are backwards or reversed, f is odd. Okay? So when you compare these, you're just going to say, are they all the same or are they all different? Right? And so look here, right? Out front, there's no sign, so it's a plus. So that's a plus, even though we didn't write it, and a minus. So they're backwards. And this one's a plus, and this one's a minus. So it's backwards. So they're both backwards, right? So both of the signs are reversed. So if they're all reversed, which they are, then your function is odd. So we see f of x is odd. All right, so that's how you would deal with an even function or an odd function algebraically. It's a little bit of work. Now, there's kind of a shortcut, though, that you can use. You might have already noticed what it is from what we wrote over here. But basically, even powers of x are even functions. And odd powers of x are odd functions. All right, so that's pretty easy. Even is even and odd is odd. Now, something that gets people into a little bit of trouble is, what about constants? So a constant whoa. An added constant like, +3 or something is even. Right? So constants are even, not odd. Like the fact that 3 is the fact that 3 is an odd number doesn't matter at all. It's a constant, and a constant is an even function. All right? And then the idea as well is, one more fact is, for functions, even plus even is even. Odd plus even, no, sorry, I don't know why I wrote that. Odd plus odd. What? Why is writing so hard? Odd plus odd is odd, and odd plus even is neither. All right, so if I write a couple functions and I say like f of x equals 12 minus 4x to the 6th, g of x equals x to the 3 plus 5x to the 5, and I say h of x equals 4 plus x cubed, and I want to know if these are even or odd, right? then all you have to do is look at the powers and remember again that constants are even. So looking at F, that's even, right? Even, right? Because it's an even power. So an even and an even is even. And then for the next one, 3, that's odd. 5, that's also odd. So it's odd and odd, which is odd. And on the last one, you've got a constant, which is even, and you've got x to the 3. 3 is an odd number, so you have an even and an odd, and that is neither. All right? So the reason it's important to know that kind of thing is because what we did up here, where we evaluated f of negative x, that's a lot of work, right? Wouldn't it have been a lot easier if we just looked at this and said 3 is odd, 1 is odd, so odd and odd, so it's odd? Yeah, right? That would be a lot easier. And so that's how you want to handle those. All right. Now, I think the last thing I'm going to do from this section is talk about what that means in terms of graphs. And then we will be done because it has been 41 minutes, 42 minutes so far. All right. So even and odd on graphs. All right. So this is actually a pretty simple idea. So an even function is symmetric left and right. We'll see if I can draw one. I have faith in me. No, I don't. Okay. I'm about to... Why can't I draw this? This is so much harder than paper, and I don't even know, I don't understand why it's harder than paper. My hand just like slips when I try to draw. That's my excuse. Okay. Okay, close enough. That is a perfectly symmetrical W, and you can't convince me any different. Okay. So this is what an even function looks like. Even. Symmetric left and right. Okay? Even function. Now, this right here, I mean, you know this, but this right here, what is that? That's the y-axis, right? And so we would say that this function is symmetric about the y-axis, right? Because that y-axis is where it's a mirror image. So I say symmetric left and right, but that is symmetry about the y-axis. Okay. Now, what about an odd function? Oh, those lines aren't even right. I'm getting worse. Okay. That. Like that. Okay. So this is what an odd function looks like. And we say that this is symmetric about the origin. Now, what's that mean? So the origin is right here, right? And why is this a graph of something that's symmetric about the origin? The reason it is because if you take a point on the graph, like right here, and you go from that point through the origin, and you keep going, you get to another point on the graph, right? And if you think about it, whatever the values are here, like if this is, I'm like, let's say that this point is 3, 1, then the point over here is 3, -1, something like that. And for every point like this, there is a corresponding point on the other side of the graph, and you get there by going through the origin. And so that's why they say symmetric about the origin. Okay? And that's an odd function. And so you should be able to look at a graph and just say, oh, that's even because it's a mirror image left and right, or it's odd because it's a mirror image through the origin. There's another way to think of it as well. Another way to think about an odd function, which is, let's see if I can do it real quick. I'm going to fix that. Okay. So there's another way to think about an odd function, which is, let's say we start with a piece over here, like that, right? Now, if you reflected it horizontally, you would have a graph like this, right? And that would be an even function. But, cross that out, if you reflect that vertically down here, then you get something like that, right? And so if you take a graph like this purple graph and you reflect it this way and then this way, and then you get something like this, then this graph right here is an odd graph. Okay? And that's another way to think about an odd graph when you're looking at it. Okay. I think that's enough. We're like 45 minutes in, 47 minutes in, and I've got more videos to make. So that is it for now. So this page here, this entire set of notes that I just drew is going to be posted online for you, as well as this video, which you know because you're listening to right now. Okay, that's it. See you in the next video.